I'm Joshua Bardwell, and you're going to learn something today. And you really are going to learn something today. You know, I try and put a little bit of knowledge in all of my videos, even product-focused videos. But today, I'm really excited to bring you a test that I've wanted to do for a long time, and I finally did it. And I'm so excited to tell you the results that I'm releasing them even though I'm in a hotel room right now with terrible, terrible lighting. It's late at night. I'm recording after work, and I can't get good video. And so I just was like, screw it. I'm just going to do a voiceover. The whole video will not be me talking over this still image. I do have video I shot from when I was doing the experiment that I'm going to cut to in just a second. But let me tell you what the experiment is. The question that it is designed to answer is this. Sometimes you get batteries and they have 14 gauge wires. Sometimes you get batteries they have 12 gauge wires. For mini quad pilots, those are the two most common wire gauges that you get. And of course, it's true that 12 gauge wires have less resistance. 14 gauge wires have more resistance. So some people say, oh, if you're a racing pilot, you absolutely have to use 12 gauge. You get more amps and less heat buildup and more watts and yada, yada, yada. But I have long suspected that that is not true. And I've got a test where I'm going to find out if it's true. Let's go to the test. Let's take a minute and explain to you what I've got set up here because the vast majority of the stuff you're looking at has nothing to do with this experiment. This is just my cluttered bench. We'll start right here with the load. This is a resistive load. These are wire wound resistors on a big heat sink. And at 4S, it pulls about 60 amps. So it's a pretty beefy, I don't know what the resistance is, but it's a pretty beefy load. We've got that wired, and by the way, all the wiring in this experiment is 12 gauge wiring. I'll explain more about that in a minute. We got it wired through this blade switch here, which is knife switch, I think it's called, which is used to make and break the circuit. And that's important because the very first time I started doing any of the experiments like this, I tried to plug in an XT60 with like a 30 or 40 amp load attached, and it sparked and shorted, and yeah, so got a blade switch. Then we are going over here into the good old Turnigy 7-in-1 megameter. This is going to tell us how many amps we're pulling. And then we go over here all the way to my power supply. Yeah, I was going to do this experiment originally with LiPos, but hey, I thought, guess what? I have a power supply. Inside here is a HP rack mount server power supply. It can do 1,000 watts at 12 volts, so we're really going to have no problem. It's way safer than using a LiPo because if it gets shorted, it'll just shut down. And in fact, I have a page on my website with instructions for how to build this exact thing with all the parts and everything. If you want to build one for yourself, I'll put a link to it in the video description. But what is the point of all of this is that I have this multimeter here, and the multimeter is measuring voltage drop, but not where you would normally think. Normally you would be measuring voltage between the positive and the negative wire here, and it would be 12 volts. But that's not what we're doing. I have one alligator clip here, and the other alligator clip all the way at the end of the wire, right where it goes into the Turnigy megameter. Now, how many volts are there going to be across either end of that wire? Well, as you would expect, it's 0 volts, right? There's no voltage drop through the wire. The wire is a very good conductor, and it's not dropping any volts. But here's the thing. As the current begins to flow, the resistance of the wire will cause voltage drop. And the more current that's flowing, the more voltage will drop. When you run current through a wire and the wire gets hot, that's energy. The volts are being converted into heat, I guess, anyway. So by measuring the amount of voltage drop, we can then use Ohm's law, our good old friend, to calculate the resistance of the wire. And that's useful because if we were to simply take a multimeter like this and measure the resistance of the wire, it's so low that it would just read 0, and we just really couldn't measure it accurately. But by using this technique, we can measure the resistance of the wire very accurately. Well, I didn't really like how infrequently that Turnigy megameter was updating, so I went and got my good old Unity clamp meter. We're going to try that instead and see if we can just repeat this test. Okay, that should be enough information to calculate the resistance of the wire. Now everything is exactly the same, except I've swapped out the 12 gauge wire going from the clamp meter into the power supply for a 14 gauge wire. And we're going to run the exact same experiment, and we're going to see how it differs, how much, basically measure the difference in resistance and the difference in voltage drop between those two wire gauges. And here it is. Whoa, it's the magic spreadsheet that you've all been waiting for. And no, I'm going to get to the results really quickly. Don't worry. I'm not going to spend hours. See, this one is 0.642 and this one is 0.4615, you see. No. But let me just briefly tell you what I did here, because some of you I know are really interested. I took the amps and the voltage drop. So I basically went frame by frame through the video looking at the amps and the voltage drop over a several second period. And I used those two to calculate, you can see the formula right here, to calculate using Ohm's law the corresponding resistance, right? So you take amps divided by the voltage drop and you get the resistance, right? Voltage drop divided by the amps, and you get the corresponding resistance. And that is how we can measure these very, very small resistance values even without, a very, very sensitive ohm meter. Without a very, very sensitive ohm meter, by running a higher current through the wire, it amplifies the effect of the resistance, so we get greater voltage drop. And you see, then we can measure the resistance more accurately. And what we can see here, these results can be used to kind of validate the test, because if these numbers were way, way different from each other, if they were just all over the place, well, the resistance of the wire hasn't fundamentally changed. Some of you will note that as the wire heats up, it does slightly change its resistance, but overall, the resistance of the wire doesn't change that much. So if we got 0.6, 0.7, 0.8, 0.9, then that would tell us that something was wrong with the test methodology, that our incoming data was kind of garbage. But these numbers are pretty darn consistent, and that I felt so good when I got this result, and I said, oh, I might be onto something here. And likewise, we did the same thing for the 12 gauge and the 14 gauge wire, and we can see that there's a substantial difference in resistance between them. The 12 gauge wire is 0.006 ohms, the 14 gauge wire is 0.01 ohms, so that's a pretty big difference. But does the difference matter? Practically speaking, yeah, we're getting to that. Some of you already guessed the answer from the video title. So then what I did is I calculated based on that. So this is the resistance per 4 feet of wire. So then I just converted that to resistance per centimeter of wire, because it's easier to think in centimeters. And then I calculated how many volts. Based on this resistance, if you know the resistance, then you could say how many volts will the wire drop and do all kinds of math. Once you've backed out the resistance, you can then go forward to calculate all kinds of things. And here are some tables that you can dig through. I'll put a link to this spreadsheet in the video description, of course, but this is if you have a 12 gauge wire and you had 3 centimeters of wire and you ran 10 amps through it, how many volts would you drop across that wire? How much lower would the voltage coming out the other end of the wire be, like going into the flight controller or the ESC, compared to what was coming out of the battery? And I did this for 14 gauge, and then I calculated the volts difference, and this is what really matters. How many more volts will you drop if you're using 14 gauge wire versus 12 gauge wire? And what you'll see, let's start with just the 3 centimeters, because 3 centimeters, that's a pretty short battery. That's like you've got it plugged directly into your PDB. Well, you've also got several centimeters of wire coming out of your battery too. So, but maybe this is unrealistically short. But what we see is that in the worst case scenario, at 120 amps, a 3 centimeter 12 gauge wire is dropping 0.01 volts less than a 14 gauge 3 centimeter wire. The difference between those two, the advantage that you gain by using 12 gauge versus 14 gauge, is 0.01 volts. That's not very freaking much. Okay, you say, well, 3 centimeters. Nobody's got a 3 centimeter battery cable, Joshua. Well, what about a 10 centimeter? Is that a little more realistic for you? And that includes, again, the wire coming off the battery, not just the wire on your quad. So at 10 centimeters, it's 0.04 volts. And that's still not very much. That's not very freaking much, honestly. It's not nothing, but it's not very much. If you really want a perspective on how much it is, what you really need to do is calculate watts. Watts are what do work. Amps and volts by themselves don't tell you anything. It's watts that do work. So if we look at the watts lost, so here's watts difference between 12 gauge and 14 gauge. And in the very, very worst case scenario, 10 centimeters of wire at 120 amps, you see that the 14 gauge wire loses 5 more watts than the 12 gauge wire. And 5 watts, to put that into perspective, A single motor can put out something like 900 or 1,000 watts. So your quadcopter as a whole at full throttle, pulling 120 amps, might be consuming 4,000 watts, of which if you're using 14 gauge wire, you will lose 5 watts. Okay, so yeah, not a very big difference, and that's the takeaway for me. At the wire lengths that we are using, and at the amp draws that we are using, the actual amount of energy that's being lost to the 14 gauge versus the 12 gauge wire is totally negligible. And this is a really shocking result for me because I've said in the past when I was doing battery testing, I have nitpicked manufacturers for putting 14 gauge wires on their batteries. I've said, well, wouldn't it be better if it was 12 gauge? And in fact, it seems the manufacturers might have known something that I didn't, which is 10, 12 centimeters. The thing is, if you're thinking about putting 12 gauge wire on your quad and you'd rather put 14 gauge, but you don't want to take the loss, just shorten it up by a few centimeters and you've more than made up the difference. So there you go. One final additional deeper detail. One of the things that people said when they saw my results was that the wire, as it heats up, its resistance is going to go up. And the amount that it goes up, this is the resistance per centimeter, it's yada, 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 temperature coefficient of copper. Basically, the hotter the copper gets, the higher its resistance is. And that means that the 14 gauge wire is going to do a little bit worse because it's going to heat up slightly more, and that's going to increase its resistance. Now, to some degree, my actual measurements to calculate the resistance took this into effect, but I didn't run the test long enough to let the wire heat up enough that its resistance substantially changed. And you can see here the resistance was pretty much the same over the whole length of the test. So then I said, okay, well, if the temperature coefficient of copper is this, then for every 10 degrees Celsius, we go up above the test. So we tested at about 20 degrees Celsius. So if the wire was 30 or 45 degrees Celsius or whatever, we would gain this much resistance per centimeter. And then what I did was I added another 10 degrees. So now if we imagine that the wire was 30 degrees Celsius instead of 20, would that close the distance in some way? And we can see here that it doesn't really, no, not really. 5.2 watts instead of 5 watts. Not much difference between them. And that's going to do it for this bombshell of a revelation that was obscured by the fact that I did not have fireworks and John Cena trumpets in the background. I just showed you a spreadsheet, but I'll tell you what, the most awesome revelations that the world has ever seen have been revealed via a spreadsheet. You tell me those guys at Oak Ridge didn't have a spreadsheet somewhere. Well, they might actually. I don't think spreadsheets have been invented yet. They had slide rules, but you get the point. If you're thinking about building a high-performance quad and you're thinking about putting 12-gauge wire on there, I don't think there's any reason for you to worry yourself. The 12 gauge wire is heavier, it's thicker, it's harder to work with. The solder pads on most flight controllers aren't really sized for it. Maybe the battery pads are sized for it, but it's always easier to work with 14 gauge wire. It's more flexible, smaller, etc. And you really are not giving up a damn thing. You're giving up a tiny infinitesimal percentage, at least as far as I can tell. Now, I am going to take the brave and bold step of making this spreadsheet public, and you guys can look through my math. I believe my math is correct here, and if I'm not correct, then I want to know. So please dig through it. You guys who are also electrical guys, and if I've made a dumb mistake, then I will own up to it. I'll make a follow-up video. I can't be right all the time. All I can do is correct the record if I'm wrong, but I think I'm right. And if I am right, I think that's a pretty cool freaking result, right? Is that cool or what? Okay, well, anyway, that's going to do it for this video. Thank you guys so much for watching. As always, happy flying.